Let's share the screen. Okay, so can you see the screen? Is it visible? Yes, sir. Right. Okay, perfect. So we talked about atmospheric pressure, right? And we discussed its relation to different things like height in air, and slightly discussed it in liquids as well. But now let's focus our attention solely to pressure in liquids, right? And so we want to understand that how can I develop a relation between pressure inside liquids uh, related to their densities, or how deep is an object inside the liquid, right? So for example, if you remember, I gave an example of density of molecules, right? So in liquid, the molecules are somewhat closely packed, at least compared to air or gas, right? So suppose if these are the molecules in water, then the pressure that any object, maybe there is an object in the water over here as well, this object will feel pressure due to these molecules, essentially, right? And these molecules are making up a liquid. So the pressure that this object, this block, experiences due to the liquid is entirely dependent on the density of this liquid, meaning how many molecules I have in a given area or a volume, right? Now, so we can clearly see that the pressure depends on the density. I'll call that rho, density of the molecules of liquid. Now, imagine if you were, we all are familiar with the idea of acceleration due to gravity and its dependence on mass, right? Now, if a planet, by mass, I mean the mass of the planet, right? So on Earth, it's higher. On the moon, the acceleration due to gravity is lower. So it should also depend on acceleration due to gravity, because all of these molecules, they would be exerting some force, right? The weight of all of this liquid will also contribute in the pressure that is exerted on this mass or on this block, right? So that's why the pressure should also depend on the acceleration due to gravity. The pressure will also depend on the depth of this object inside the liquid, because suppose if instead I have, so I'll draw some more molecules, right? And instead the object was here. Now let's say the object is somewhere over here. So it would experience pressure from more number of molecules that are above it, and hence the pressure would be higher. So the more deeper that the object goes, so the height that we are measuring is from this level, right? So this is known as sea level. And at sea level, we reference it as to height being 0 meters. And then we increase the height downstairs, right? So as you go down, it becomes 1 meter, 2 meters deep, 3 meters deep, and so on. So the more deeper you go down, the more number of molecules of liquid you have on your head. And altogether, the more number of molecules I have, the more pressure they would be exerting on my head. So that means that the pressure should also depend on the depth of the liquid, right? So this gives us an equation, or you can say a formula, to compute pressure in liquids, right? And that is rho g h. And this is an expression that we can use to compute or solve any type of a problem that is regarding to liquids and pressures, right? So any question?
No
so far?
questions.
Okay. Uh, uh, is uh, is it clear for everyone how? So what I'm asking you is, do you understand how pressure depends on density of the liquid? How does it depend? Why does it depend on the acceleration due to gravity and the depth of the object inside the liquid? All these three things are clear. All
Yes,
right.
sir.
Okay. Okay. Perfect. Now, let's try to use this thing, right? And suppose that you have a container. Let me draw this container, and it's opened from the top. Remember, whenever if the container is specifically mentioned that it's open from the top, it will always be experiencing whatever is inside the container. Suppose I'm going to suppose that there is water inside this container. So the density of the water is 1,000 kilograms per meter cube, right? So suppose that there is water, and if it is completely open from the top, that means that there would be always some atmospheric pressure on the water, right? Due to the atmosphere, due to the layer of the atmosphere that is on the on above the surface of the earth, right? So we talked about atmospheric pressure and where does it come from. Can anyone who was there in the last class uh, tell me where does the atmospheric pressure comes from? Why is there atmospheric pressure?
The air
Why does it
molecules,
exist at all?
collide with the water or an object. That's
Right,
why.
exactly, right. So because yeah, exactly. So the atmosphere is made up of molecules, atoms, different types of elements. Nitrogen, we have nitrogen gas, oxygen gas, and so on. And all those gases are made up of molecules, and those molecules would collide with water and exert the pressure. This pressure is called the atmospheric pressure. What was the value for the atmospheric pressure in pascals? Suppose you have to give me the answer in pascals. Does anyone remember?
I think it was one atmospheric, but I don't remember in
Yeah, it
Pascal.
was one atmospheric exactly. And but one atmospheric is just, you can write it as 1.0 into 10 raised to power 5 pascals, right? And normally it's 1.01, but that 0.01 does not make a very big difference. You can take it as 1.0 into 10 raised to power 5 pascals, right? And pascals, by the way, is the SI unit that we use in our calculation. So if your units are for density, if your units are kilograms per meter cube, for acceleration due to gravity, your units are meters per second squared, and for the height, your units are meters, then these would combine together to give you a unit of pascals, right? So that's the SI unit. They combine to give you a unit, right, in kilograms, meters, and seconds. And that new unit, we define it, we call it Pascal, right? Okay, so okay, here we have a question. Now suppose, let me use another color. Let's use green. I pick any point in this water. Suppose this is a point, and I'll call it, because P is used for pressure, I'll just call it some X. And say that this point X is, let me change the color. From the bottom of the container, it is at some height. Let's say this is 2 meters, and from the surface of the water to the point X, the height is, this is 2. Let's make it a total of 10, and this would be 8 centimeters. Right. So this is what you are given, and you are told that in water, sorry, in this tank, the liquid is water. So this is water. Can you tell me what would be the density of this liquid?
100 kilogram per meter square, a cube.
1,000, right? per meter cube, 1,000 kilograms per meter cube, right?
Yes.
Okay. 1,000 kilograms per meter cube. So that would be the density. I got that because we know that the density of the water is 1,000 kilograms per meter cube. It's a density that you expect people to know. Density of air and density of water. Density of air is very small, but density of water is 1,000 kilograms per meter cube. So you're expected, probably even in your exams, you would be expected to know this density of water, right? Okay, so if now in the
Sir, I had
question
a
it's just specific.
question.
Yeah, sure, go ahead.
Sir, is the density of water the same throughout the body for the body? Like
It
um
is exactly, and that concept, we'll talk about it. That's why we say that water is incompressible. You cannot compress water, right?
what about other materials?
Yes, there are
Its
different types of,
density
right? So
change?
you have, yes, so there are types of materials that there. So, for example, a gas, you can compress a gas, you can expand a gas, right? Its
Yes,
density
sir.
changes, but for a water, its density remains a constant.
Okay,
And the
sir.
reason for this lies again in the atomic structure of water, or liquids or gases. Liquids, mostly all of the liquids are incompressible, and the reason is because their molecules are, they're strongly connected to each other. You can say the interaction between the molecules is stronger compared to the interaction of the gas molecules. There is almost uh, no interaction in gas molecules. They're mostly free, right? And because of that, they can, the number of molecules occupying a particular volume can change for a gas because they can easily escape, right? Because they're not bound to each other. But for a liquid, the molecules are bound, closely connected. There is a strong, you can say, bonding between these molecules. Compared to gas, the bonding is strong, and hence they cannot escape. So they cannot occupy less volume. Some number of molecules, they cannot occupy less volume. The volume that they will, the specific number of molecules would occupy a given volume all the time. So, and that's density, right? So the density for liquids is constant. It's a fixed. Okay. Does that answer your question?
Yes, not
Okay,
mine,
perfect.
but I heard the question, so
Yes, sir.
Sorry, someone was saying something. Is there any other question?
No, I have no
Okay.
Yes.
question.
All right. So, okay, so this is the density of water then. And what I want to compute is, let's try to figure out the pressure. Now, listen to this carefully, right? So the pressure of a liquid, pressure of liquid at X, at this point, right? So at point X. So that's the first thing that we want to figure out. So can someone tell me quickly, what would be the pressure of the liquid at X?
80,000 Pascal.
80,000, right, 80 kilopascals, right? Because when you, so you use 10 sorry, this was meters, right? So you use 10 meters and 10 for value for G, and you used 1,000, right? So to compute it, it's rho GH, right? Because we're talking about liquid, right? So pressure in liquids is given by this equation. So we have 1,000 kilograms per meter cube into 10 meters per second squared into 10 meters. and this gives you, sorry, this would be 8, right?
Yes,
Why would this be 8?
because the point is at 8.
Yes, because the height, exactly, right? So the height that we are measuring is from this one, and from here to here, the height is 8 meters. And this would be 80 kilopascals, right? Or 80,000 pascals. Now, suppose the next thing I want you to tell me is the total pressure that would be experienced at point X. Would it be the same 80 kilopascals, or would it be different?
It would be different.
Oh, so right. So what would you expect it to be? How would it be different?
Because in the formula it requires height. When you change height, the product will change.
Okay, and no, but I want this total pressure at X, and at X the height is still the same, right? It's 8 meters. The point X never moved,
Okay, and
right? So the
So,
point X is
Professor,
still at the same height. Yes.
yes, sir. The pressure exerted by the atmosphere, I think we have to add it.
Sorry, the pressure exerted by
The atmosphere.
the atmosphere. Exactly, right? So because there at point X there are above it there are two different types of matter. One is liquid, which is water, and one is the atmosphere. Atmosphere is also exerting because there are molecules in the atmosphere and there are molecules in water as well. So there's the total pressure that would experience would be the sum of both of these pressures, right? So we would add this pressure of liquid plus pressure due to atmosphere, which was this value, and this would give me the total pressure. So you just add 80 uh, kilopascals to 1.0 into 10 raised to power 5 pascals, right? Okay, so is it clear?
yes, clear.
Yes, sir.
Okay, perfect. Right. So any question from this discussion of pressure in liquids?
No questions.
All right. Okay. So now we are going to talk about how does the pressure transfer in a liquid, right? So I'll call it transfer of pressure in liquid. Transfer of pressure in liquids. Now there is a law that was also given to us by Pascal. So it's called Pascal's law. And this law dictates how would the pressure be transferred from one end to another end in a liquid. Now, Pascal's law states that any liquid, so it could be any liquid, would exert an equal amount of pressure everywhere, right? So liquid exerts equal amount of pressure in all, or you can say on all of its surface. So what that means is, I can give you an example. Suppose you have, again, I'll give you this example. There is a water, right? So this is water. And I have in this water, suppose I have a block. Now this block would experience a pressure in all of its surfaces. So on this side, this side, this side, and this side. And on all of these sides, the pressure that this block would feel would be exactly equal. So for example, if from top it feels a pressure of, you can say anything, 10 kilopascals, then on all the directions it would feel the same pressure. Now, this can be applied in understanding the transfer of pressure by, if I say that if a pressure is exerted, you can say from one end, and for this I need to give you an idea of something that's called a, what do you call? I think it's called a hydraulic press, right? And it's, so I'll try to draw it first. Right, and so something like this. Right. Okay. So now there could be there is a piston over here, right? And there is a piston over here. A piston is just something that you'll will use to push or pull, or you can say apply pressure to this piston. And there is some liquid in this region, right? Now, suppose that I apply some force on this side, right? That would mean, because I'm applying a force on this piston, I'm applying some pressure, and that pressure would be exactly equal to this force divided by the base area of this piston. So I'm essentially applying a pressure on this point, right? What would that do? That would exert an equal amount of pressure throughout this liquid, right? And so at every point in this liquid, an equal amount of pressure would be exerted, and this liquid, it would rise over here, right? So you can say that if a pressure is exerted from any one of the ends of this thing, the liquid will transmit the pressure exactly equal in all the directions. So it will not be like that some of the pressure is eliminated or lost somewhere. Every point in this liquid, it would experience the same amount of pressure, right, in all the directions. And why is that? Can someone explain? Can someone just give take a guess? Why is that so? And I'll give you a hint. The hint is that this is mostly only applicable to liquids, right?
Because the atoms are more closely connected.
Exactly, right. So it is because of the incompressible property of liquids, right? So no pressure is lost during the transfer due to the incompressible nature of liquids, right? So does everybody understand that?
Yes.
Yes.
All right. Incompressible nature of liquids. All right. So that's Pascal's law. And if that is the case, then I'll take any 2 points in this diagram that I made, right? I'll use another color. So suppose I take this point and I take this point. These 2 points are, I'll call this A and call this B. Now, you tell me, if the pressure at A is some PA, then what would be the pressure at B?
Also PA.
Exactly, right? So the pressure at A is exactly equal to pressure at B. And this, using this thing, this really gives you an expression, and this expression can be written because of the Pascal's law. Now I can expand it even more by saying that the force experienced or exerted at point A divided by the area at A is exactly equal to the force exerted at point P per unit area at B. And this expression that, or you can say this equation, now you can use this equation to compute whether you want to compute area or what force that was exerted in this kind of a system. This system is called a hydraulic system. And for any hydraulic system in your exam or in a test, you will always use the help of Pascal's law to compute either area or force. That is, you can say, produced because of this hydraulic press, right? So this is an equation for hydraulic press systems. So what do you understand what would be a hydraulic press system?
Yes, it would be two pistons or one piston compressing an object or liquid.
Right. Okay. So this hydraulic press system is used. In fact, it's very strongly used in the braking system of a car, right? And so anyone has any idea how does, so for example, you're all familiar with, everyone is obviously familiar with a car. You know, when you press on the brake pedal, the car slows down and eventually comes to a stop. Now that is only possible because of our study on pressure in liquids. And then it's the application, you can say it's the application of Pascal's law. So does anyone have any idea how does that work?
So
I
maybe
don't-
the pressure we apply on the brake, um, the brake it's connected to some water body,
Yeah.
some liquid.
Yes, right. So exactly right. So it's something like this. So suppose that I'm going to draw a figure, right, of a car brake system. It's going to be a very simplified figure, car brake system. And the figure, it looks like this, that this is the piston, and the piston in this case is our brake pedal, right? And here we have this system. It's like this. There's a pipe going like this, and then you have another piston, and that is a very quite large piston, because now this one will be used to apply pressure on the brake discs, and there is some, it exerts some force from here. And then this is, you can think of this as your brake pedal. This is what you push, right? Now you'll push this with some force, so you're applying some force on a particular area, and in this thing it's completely filled with what's called a brake fluid, right? Sometimes it's also called brake oil, but it's a brake fluid. And you can see it's always, you have to check its limit, that if it's sometimes you have to check that do I have enough brake fluid? Because if you don't have enough brake fluid, then the system will not work, because the system entirely depends on this fluid and the pressure that is applied to this fluid, right? So what happens is, when I push this brake, you're basically exerting a force on this piston, right? And when you when you exert that force is applying pressure onto this brake fluid, right? And because of the Pascal's law, that pressure is going to be transmitted or transferred throughout this system, or you can say throughout this entire liquid, right? It starts from here and then starts getting transmitted up until this point. And from here where it goes is, it goes to the wheels. And on wheels, there is a brake disc attached. So what this pressure does is, it pushes against those brake discs, and those brake discs then essentially pushes itself onto the wheels. So the wheels are spinning, and the brake discs pushes against that spin, so that will cause the spinning to stop, right? So because you can imagine, if something is spinning in front of you and you put your hand on top of it, it will slow down due to the friction, right? And that's how the car brake system works. And that's why when you push on the brake pedal, this is what's happening behind the scenes, you can say, and your car eventually comes to a stop. Now, because we have this figure, we can do a problem for this figure. Let me see how much time is left.
2
2
minutes.
minutes. Hopefully, we can do this problem in those 2 minutes, right? So actually, we don't have much space, so I'll move this to this side, right? And now, suppose this is the same thing that you have, right? So you have a car system, and this is an example of a hydraulic press system. And suppose that I exert a force of 20 newtons on the brake pedal, right? And this would result in some force being exerted on this part of the piston, right? Suppose that the brake pedal has the area of this brake pedal is computed to be equal to 5 centimeters squared. And this piston is measured to have an area of 25 centimeters squared. I want to compute this force F. First, tell me, would I be able to compute this force F if
Yes, sir.
Pascal's law was
Yes.
invalid?
Yes.
If Pascal's law was invalid.
No.
Okay,
No.
right? So you would not be able to compute this force F if Pascal's law did not hold true. So it's the Pascal's law that will allow you to compute this force F, which means that I'll use the equation of the Pascal's law, which we can see over here, right? So everybody understands that?
Less than
Yeah.
1 minute.
Okay, right. So now using this equation, it's very simple. This is the force at point A. You can say this is point A and this is point B, and this is the area at point A. So you have 20 newtons divided by 5 centimeters squared, which is equal to force at point B, which we do not know. But the area at point B is 25 centimeters squared. Now you can rearrange this expression for FB as 20 newtons